I'm your host, Eric Geisels. I'm a professor of finance at the Keenan-Flagler Business School, and professor of economics at UNC Chapel Hill, and the faculty research director of the Rethink Labs at the Keene Institute. This is our third webinar series. I have the pleasure of introducing today's speaker, Román Orús. Román is the Ikerbasque Research Professor at the Donostia International Physics Center in San Sebastián, Spain, and he's also the co-founder and CSO of Multiverse Computing, one of the first startups worldwide providing quantum computing solutions for the financial sector. We're in for a treat today in the sense that Román is not only going to talk about his paper on dynamic portfolio application with quantum algorithms. What he's also going to do, which is really interesting, is that he's going to look at implementations on various platforms. As we know, quantum technology is still in a flux, and it's somewhat unsettled ultimately which platform will be used for what kinds of applications. And one of the nice features of Román's paper today is that he will look at implementations across a variety of platforms for quantum computing in portfolio allocation decisions. Before we start, just a few housekeeping notes. At the bottom of your screen, you see a Q&A. Please feel free to write a question, and at the end of Román's presentation, we will address some of the questions from you participants. Thanks again, and I'd like to pass on the word to Román. Welcome, and I'm looking forward to your talk.
Okay, thank you. So thanks a lot for the nice invitation to be in this webinar series. It's I mean, one of the good things of doing things online is that one can actually attend and go to many more talks than before.
That's right. So, there are too many, perhaps.
Exactly. Now maybe there are too many. Yes. Excellent. So yeah. Again, thanks a lot for the invitation. Let me share my screen. Now it should be working.
Great. Yeah. You're all set.
Okay. So in this talk, I want to tell you about some recent paper that we posted together with our friends from BBVA, which is a bank in Spain, where we implemented different optimization algorithms, both quantum and classical, for a classical problem in finance, which is portfolio optimization, okay, dynamic portfolio optimization. I will be more specific about the problem later. And as we were saying before, so we did a comparison between different quantum platforms, okay, and we did these calculations with real data. So if you are interested, this is the archive reference for the preprint of the paper, okay, which was submitted for publication. We just posted this before the summer, and yeah, let's get started. So first, maybe just to let you know where we are working. We are working in San Sebastián or Donostia in Basque language. All right. This is a small city that is up here in Spain. It's very close to France, actually. So it's only 20 kilometers from the border to France. And you know, it's a very nice destination. So if you ever want to come to visit us, please, you are very welcome. People here not only go for lunch and go for surfing because, you know, we are just next to the ocean. It's a typical place where people come from holidays. But it turns out that we're also doing quite some interesting quantum science here. So there are several research centers, in particular the IPC, which is a theoretical physics center where we have lots of people doing quantum technologies, and also Multiverse Computing, which is a startup that we just started, which is on quantum technologies and quantum algorithms for finance. Okay, so it's not a bad place for coming for a visit. Feel free to come. Okay, let's start with this basic question because I'm not sure about the background. that you guys have. So if you mostly come from finance, of course, quantum mechanics is a complicated thing to understand, but at least we can get an idea of what are the basic, what is the basic intuition. No? So what is quantum computing? Well, it turns out that the idea is quite simple. This dates back to actually some intuition by Richard Feynman, which was a very famous physicist. The idea is to use quantum mechanics to process information. So classical computers use the classical laws of mechanics to process information, all right? Now, quantum computing is different in the sense that what we are going to do is to store the information in quantum systems themselves, okay? So for instance, in the energy levels of an atom or an ion, let's say. So once we encode information in quantum systems, we can use quantum mechanics to process this information. And it turns out that following the laws of quantum mechanics, we can do many things that otherwise it would just be impossible to do in classical computation, okay? Turns out that we can do calculations that will otherwise be intractable with just a conventional computer. Well, nowadays, we start to have the first prototypes of quantum processors. So there has been a huge, I would say, leap forward in the last 5 years or so because of some important experimental developments. And thanks to this, quantum processors have gone from being just, a lab experiment in some universities to something that is scaling up. And right now, we start to have the first quantum processors that are starting to be serious, okay? So, here are some companies that are doing quantum processors. There are different types of quantum processors. For instance, there are processors based on it's called quantum annealing. These are processors that are only good at solving one particular problem, and this problem is optimization. There is one company that is doing this type of processors. This is D-Wave. All right, this was the first company that was commercializing quantum computers, maybe much earlier than all the others. And at some point there was a lot of people talk a lot about this company, for good or for bad. But nowadays it's true, they have this processor and it's, one can do things with it. Other types of quantum processors that the people are commercializing nowadays, are based on what is called universal quantum computing, or what they call universal quantum processors. These are the closer thing that you will imagine to, say, a computer based on logic gates. And these are based on quantum gates. These are the types of processors that people like IBM or Google or Rigetti, which is another startup in the US, are developing, okay? And well, the list here is not exhaustive. There are by now many more companies doing quantum hardware. Now, the important thing here is that this quantum hardware is improving every day. It means that right now we can start doing things, proof of concepts and so on. But the prospect is that this is gonna get better, and people need to start getting prepared for what is coming. All right, let me show you a nice example of things that one can do with a quantum computer, or with a quantum processor, at least with what is provided nowadays. This is an example. It's already an old example. It's from 2017. It's a calculation that was done using D-Wave, this type of quantum annealer processor that is very good at optimizing. And this was a collaboration between Volkswagen, the car company in Germany, and D-Wave. So what they did was the following. They did some traffic optimization. They went to Beijing and they optimized the traffic, essentially the routes of the taxis in Beijing, all right? They did this using D-Wave. You can read the results here. And then it turns out that they also did a very similar proof of concept in Barcelona. They optimized the taxi demand, the routes of taxis depending on the demand according to GPS data in Barcelona. These were two early applications of the D-Wave machine. And it was a very nice collaboration. And in my opinion, this is starting to show that some of these processors already start to have some commercial value. And of course, there are many other examples. Feel free to have a look at this website, where there are actually many interesting talks about applications of D-Wave in real life problems. Okay, Now let's talk about why do we need a quantum computer? So it turns out that quantum computers are going to be useful for many different things. Of course, they are going to be useful for material science, because materials, at the end of the day, they are made of molecules and atoms, and these are quantum systems. And if we want to simulate a quantum material, then we better use a quantum computer, because otherwise the equations are just too complex. Of course, finance, which is what is going to be interesting for us today. Chemistry, of course. Chemistry is all about quantum mechanics. Optimization problems, as I was saying. Nature tends to be in the minimum energy of some configurations, and this is nothing but an optimization problem. For machine learning applications, we are starting to understand that turns out that with quantum computers, we can speed up quantum machine learning applications. And I like typically to say that the most important application of a quantum computer is yet to be discovered. So quantum computers are going to be important for many other things that I'm not listing here. But the most important thing that we will do with quantum computers, we just simply don't know. This is like asking, Alan Turing in the 30s whether Twitter will be the most important application of a classical computer. So of course, Turing didn't have any idea about Twitter at that time, no? So here, this is the interesting step in which we are. So we need quantum computers working in order to understand what they are going to be useful for, all right? But right now, we can already identify quite a few places where we can use them. Here we are going to be talking about finance, and of course, this is going to be interesting for different people. It's going to be interesting for banks, for financial institutions, for central banks, finance departments of very big companies, rating agencies, regulators, tax offices that are looking for fraud, people looking for money laundering, all these sort of things. So essentially, anywhere where people use mathematics or computer science algorithms in finance and economy is going to be hit by quantum computing. Because, as I will explain in a second, these are exactly the type of problems at which quantum computers are good at, the ones that we find in finance. All right, so why quantum computing for finance? Because it's full of hard, I should add here, mathematical problems. That's the point. Now, typical problems that we find in finance. Of course, this list is again not exhaustive, and there are many other types of problems. I'm pretty sure that you know much more than me about this, but at least here are three that are quite generic. The first one is this one: which assets should be included in an optimum portfolio, so portfolio optimization. All right. And the broad approach to solve this is through optimization models. Now, another type of question that we may have in finance is how do we detect opportunities in the market? Can we predict what the market is going to do, and how can we take profit by trading these opportunities? Now, typical approach that people are doing nowadays is machine learning. There are others, okay, but machine learning in finance is getting quite popular. And finally, how do we estimate the risk of a portfolio, or the risk of a company, or the risk of the whole financial system? This is done typically using Monte Carlo methods, all right? Typically, let me stress that this is again not exhaustive. Well, it turns out that in these three broad families of problems, quantum computing can help. So if we are talking about optimization, of course, quantum computing is very good at optimizing. So there are quantum optimization algorithms that we can use to try to find solutions either more efficient or perhaps better solutions, okay? So that we don't fall into local minima and so on. In machine learning, well, the same story. There is a whole research field that is called quantum machine learning, where we are understanding how quantum computers can help to accelerate and to improve the performance and the accuracy of the solutions of typical machine learning algorithms, so regression, the data classification, and so on. All these can be improved using quantum computing. And finally, with Monte Carlo, that's also something that can be improved with quantum computers, because there is an algorithm that is called quantum amplitude estimation that can be used to essentially do the same calculations that we will do with Monte Carlo, but quadratically faster. All right, so here we get what people in computer science call a square root speed up. This is also important, for instance, for the people doing option pricing. They do lots of Monte Carlo there. With a quantum computer, a priori, if you had many qubits, you would be able to speed it up by a square root using this quantum amplitude estimation algorithm. Now, there is a lot to be said here. In this talk, I'm going to focus on quantum optimization. Well, why? Because it's kind of the most canonical problem that we can find, optimizing a portfolio. And let's see how well we can do. So this talk is going to be about this paper, as I was saying before. Here you have the abstract. It was a collaboration with BBVA, which is one of the top banks in Spain and in the world, actually. Now I don't remember exactly where in the list it is, but it's one of the top. You know, they have a bunch of people there that they want to explore quantum technologies. They are very interested in that. And we did a collaboration with them on this dynamic portfolio optimization problem. All right. Let me start with the conclusion of the talk, which is that we were able to solve the problem with real data for the first time using quantum processors. Because so far this problem, I mean, people had proven that this was possible on a quantum computer, of course, but with very few assets and essentially with toy models, because, you know, because of the capabilities. We were able for the first time to put real data into the processors, all right? And we also did some interesting comparison between different algorithms and different hardware platforms, like quantum and classical. So we tried things like BQE, which is a type of quantum algorithm. I'll say more about that later. Also about D-Wave, which is a quantum annealer. And also about some quantum-inspired optimization techniques, which are classical algorithms that are inspired by quantum computing. And again, I will be more detailed later. But specifically using something that we call tensor networks, which is a type of algorithms that we have been using in physics a lot. All right. Good. Let's move on. So let's talk about quantum optimization. If I have an optimization problem and I want to solve it with a quantum computer, as is the case, well, there are different options that I could choose. Nowadays, these are the three most popular approaches. Probably there are more, but these are the three most popular ones. The first one is quantum annealing. This is, again, this type of quantum processor that is only built to solve optimization problems. And the idea of quantum annealing, well, at least the physical idea, is very similar to that of, say, simulated annealing in classical algorithms, but with a few subtleties. So I will not enter into the technical details of how quantum annealing works, but you should think of quantum annealing as a way of finding the optimal or the minimum of a cost function in some very complicated landscape of minima, all right? Essentially by tunneling between the different minima. You know, in quantum mechanics, we have something that is called the tunnel effect. And just by using this quantum tunneling, we are able to search for actual minima in a very complicated landscape. So this is just to get the intuition of what quantum annealing is doing. But there are other options. There are two algorithms that are becoming very popular nowadays. These are called the quantum approximate optimization algorithm, or QAOA. I think the people nowadays call this QAOA, because the guy who proposed this called it QAOA, and then, you know, it just people just stick to this notation, so that's fine. And the second, and the third one is the variational quantum eigensolver, or VQE. Now, these two algorithms have a lot in common. They are algorithms that run on universal quantum processors, such as IBM-Q, and they are hybrid approaches. So they are based on a quantum circuit that I just built. I just ran it on my quantum processor. And this quantum circuit has some variational parameters. And the idea is to optimize these variational parameters in order to minimize, you know, some cost function, all right? These are hybrid algorithms because they have a quantum part and a classical part. So the quantum circuit is quantum, of course. Now the minimization of the parameters of the quantum circuit is classical. This is done, for instance, using gradient descent or some other classical algorithm. And this is very interesting because this type of hybrid quantum classical approach it looks like it's going to be one of the very first applications of these early quantum processors that we are building. This is very promising. Well, for the sake of this talk, we use these two approaches. We use quantum annealing, in particular the machine provided by D-Wave, and we also use variational quantum eigensolvers. And in particular, we tested this in the machines by IBM. Okay, now let me talk about quantum-inspired optimization. Now, what is this? These are classical algorithms. It means that they run on conventional computers, such as my laptop, okay, that I have right here with Zoom. So I could run it here. But these are algorithms that are inspired by how quantum computers work. All right. Here are three different algorithms that people nowadays call quantum inspired. The first one is digital annealing. This is actually a processor that has been built by Fujitsu. What they do is they simulate how the quantum annealer works, but where the quantum annealing, for instance, does a tunneling, then Fujitsu comes and puts a wire. All right, sort of. Let's think of it a little bit like that. So it's entirely classical, but it's trying to simulate at the hardware level what the quantum annealer is doing. And it's working very well, okay, for solving optimization problems. Now, Microsoft has also a quantum-inspired optimization toolbox that is based on some, algorithms. It's some complicated form of quantum Monte Carlo. These were programmed by some computational physicists that are highly skilled. Okay, this. And then the one that I will be talking about today is Tensor Networks. That's the one that we used in the paper that I want to talk about. The idea of Tensor Networks is about, well, Tensor Network algorithms is a family of algorithms that we have been using in physics for the last, I would say, 20 years or something, 30 years or so, perhaps. And recently we realized that we can also apply them to solve optimization problems in industry. And also to improve machine learning algorithms. So, they are inspired by how quantum systems behave. They were originally developed to simulate quantum systems of many particles. And recently we understood that the same type of technology can be applied to solve complicated optimization problems in industry, for instance, in finance, all right? And the same story for improving machine learning algorithms. So there is a lot of technical details about Tensor Networks. I could give you many talks about it, but I will not do it. If you're interested in learning more about that, about them, just let me know. Feel free to drop me an email. Or you can also have a look at this review that I wrote recently for Nature Reviews Physics, 2019, about Tensor Networks and some recent applications. Okay, let's move on. Good, let's talk about the problem. So the problem is dynamic portfolio optimization. We want to find the optimal trajectory in the space of portfolios that of course optimizes the returns, maximizing the returns, let's say, taking into account possible constraints. Possible constraint could be transaction cost, all right? Now, mathematically, this is gonna be my return. So I have a number of assets, all right? And now I have a weight, let's say a percentage of how much of each asset I have. And I just organize this as a vector. Now this vector is gonna be this omega here. This is the asset, these are the asset weights. And this is a vector, all right? Now the return is gonna be this quantity here, where this vector here, the T means transpose, are the forecasted profits. This I can compute it from the prices. I will explain later. But these are the logarithmic returns for each one of the assets. And at the end, since they are logarithmic, I can just do the sum over all the different trading times. And this is a total return of the portfolio. Now the risk of the portfolio can be computed using this formula where this object here is a matrix and this is the covariance matrix. So for you finance guys, this is nothing but the typical, standard portfolio. I think they call this Markowitz portfolio optimization, right? So this is very standard. All right, now constraints that we are going to impose are the following. These are the first two that we are going to impose. First, we are going to impose that we are investing a total amount K, okay, on the whole. So this is fixed. The second constraint is that there is a maximum allowed investment for each asset, and this is going to be K prime. All right, we could relax these constraints, but well, you know, so our collaborators wanted to do it like that. And of course, well, here I just defined some renormalized weights where I'm just dividing by the total amount of investing, so that the sum of these W's here at each time t, the sum of all these W's here should be at 2. All right. All right. Now here is the first constraint. Well, the third constraint that we are going to impose. These are the transaction costs. This is, you know, every time that I change the composition of my portfolio from, say, trading time t to trading time t plus 1, if I'm changing the composition of my portfolio, I have to pay a percentage of the money that I'm moving, all right? This is what is represented by this quantity. At every time t, there is a percentage, this nu, of, you know, the total amount of money that I'm moving, all right? Well, it can be just written in this way, and there is an absolute value here. Notice that, because, you know, this doesn't depend whether I just sell or I buy an order. The fact is that there is a transaction. Now, this absolute value is fine for some algorithms, but is not so good for others. For instance, if we were using BQE or QAOA, this will be fine. For tensor networks, it should also be fine, okay? For quantum annealing, it's not so nice. So one needs to think about tricks to implement this absolute value in some other way. What we did for the sake of simplicity was to approximate it. I mean, there are tricks of implementing this absolute value using extra qubits, all right, and some extra resources. But what we did also in order to simplify the calculations was to approximate it by a quadratic formula. So we just did a quadratic approximation of this absolute value, like that, where we have a matrix here, lambda. The approximation is in the range where, you know, in the domain of this, of our variables, which is the weights of each asset. And this matrix here, we call it the matrix of transaction cost, and it's usually diagonal. This, by the way, is also one of the approaches that was used in the first, I think in the first paper by Marcos Lopez de Prado, where he proposed how to do quantum optimization for dynamic portfolio optimization. I think he also did something, well, he did exactly this, okay? But here our motivation was that otherwise, you know, this absolute value was complicated to put it on a quantum annealer. So we just approximated by a parabola. All right. So at the end of the day, this is our cost function. In physics jargon, we call this Hamiltonian because the Hamiltonian is the energy function and we want to minimize the energy of our system, okay? For you, this is a cost function and we want to find the minimum. Now, there are different ingredients here. Most of them I already explained. You know, we have here the total return. So we have to minimize minus the return. So it's like maximizing it, okay? Now we have here the risk. There is a parameter here, gamma, that we call risk aversion, and it controls the volatility of the final portfolio, of the trajectory that we find. We can tune the volatility by tuning this parameter. The larger gamma, the larger the volatility. And then there are the constraints. First constraint is going to be transaction cost. Since this matrix of transaction cost typically is diagonal, well, this is my quadratic approximation. And finally, there is the normalization constant, that the sum of all these omegas has to add up to 1. And that's actually what we are imposing here. This is a vector of ones, all right? And this is a Lagrange multiplier. We use Lagrange multiplier to, you know, to add the constraints into the optimization, into the cost function, all right? Now, these Lagrange multipliers are also going to be hyperparameters of my optimization problems, and in the end, I will have to fine-tune them, and also optimize over them. But that's, in principle, that's something that we can also do. So this is my cost function, and important, we want to minimize it. Now, notice that this is different to, say, optimizing in what the people call the Sharpe ratio, which will be the returns divided by the square root of, you know, this object here, which essentially is the volatility. So it's not exactly the same optimizing the Sharpe ratio than optimizing this cost function, okay? And this is something that we notice from our simulations. There are slight differences, and depending on what you want, maybe you want to use one approach or another. Here we stick to this. All right. So this was a completely generic formulation. So far, I didn't say whether my variables were continuous or discrete. Turns out that this makes a very important difference. If the variables are continuous, then you can work with derivatives, integrals, and continuous calculus, and it helps a lot. There are some cases, for instance, if there were no transaction costs, the system will be exactly solvable. But however, everything gets more complicated when the formulation is discrete. And this also makes sense because transactions of money go in chunks, all right? We implement the discrete formulation. This is also natural. It means that we pick up our variables and decompose them into a digital, with a digital notation. So for this, we use a number of qubits, all right? And this is how we do it. For every weight, we use a total of nq qubits, all right? Because these are quantum bits to represent the quantity, and this is gonna be discrete. So the total number of qubits that I'm going to need to optimize this formula is right here. So I'm gonna have nq qubits, which is the qubit depth for its weight, all right? For every time t and for every asset n. Now it turns out that there is number of trading steps is say nt, all right? And the number of assets is capital N. So the total number of qubits is here, n times capital NT times capital NQ. All right. Now, if you pick up this discrete formulation and plug it into the formula up here, you end up with what the people in computer science call a quadratic and constrained binary optimization problem. It's a formula that you have to minimize, and the variables are bit variables, either 0 or 1, all right? Now it's quadratic because it's an optimization formula over bit variables, 0 or 1. Unconstrained because a priori all the constraints are there. And it's binary optimization because, it's binary optimization because it's either 0 or 1, okay? And it's quadratic, because it's a quadratic form. It's of the form x times something times x. So it's like a parabola, all right? In physics, we like to say that this is an Ising problem. It's completely equivalent. But in physics, we pick up the qubit variables and do this mapping here and re-express the same cost function in terms of variables that can be either +1 or -1. And then it turns out that this is what in physics is called the Ising model. It's a model of a magnet, a magnetic system. We know in physics that finding the minimal energy configurations of these magnetic systems is an NP-hard problem. Well, this is exactly what we did here, okay? So in physics, we like to think of these problems as Ising problems, but these are two completely equivalent formulations. And in fact, if you have ever used D-Wave, you know that you can specify your problem either as a QO or either as an Ising magnet. Okay, independently of how we formulate the problem, this is an NP-hard problem. It means that finding the ground state of this system is extremely hard. There is no known classical algorithm that can find it in polynomial time in a number of bit variables, all right? And that's why we want to use quantum computers. Okay, so here are the methods that we are going to be using. First, some classical methods. Here we were not I'm pretty sure that there are much better options than this, but this is what we tried. We tried Gekko, which is a library of optimization solvers for Python, and also exhaustive solver. Exhaustive means brute force. Let's look for all the possible options and see how, options. No, I should not say options here. No? So let's look for all the possible configurations and find the best one exhaustively, brute force search. Then we also did quantum annealing, and in particular, we use D-Wave hybrid. This is a hybrid approach that the D-Wave guys provide, and it's a hybrid approach between quantum and classical. Essentially, the problem, I think it's divided into chunks. The chunks are, sent into D-Wave processor, and then there is a classical recombination at some point. I think it works like this. But it's quite nice. and it allows you to go to solve problems that of much larger size than what you will be able to do only with the quantum processor itself. Okay. In particular, we use the latest available D-Wave processor, 2000Q. There should be an E1 coming soon, but we didn't use that. We also used universal quantum processors. It means using quantum gates. Here we use IBM-Q up to 12 qubits, and the algorithms that we implemented was the variational quantum eigensolver, and then a version of the variational quantum eigensolver that is a little bit improved. We call it VQE constraint. It's very simple. Essentially, we use VQE at every time step to find a set of pretty good portfolios, and then use a classical algorithm to recombine them into an optimal trading trajectory. This is a hybrid algorithm that we tested also. And finally, quantum-inspired algorithms. We use a tensor network optimization algorithm based on, some tensor network that is called matrix proof the state, something that in physics we use quite often. And here the simulations were done with this laptop, okay, with the one that I'm using right now. So of course, they can be much more improved because I need into some high PC cluster. But no, I just run everything on my MacBook Pro. All right, here is the data that we use. So BBVA provided us with data for the past 8 years for 52 assets. There was a little bit of everything in these assets. From the prices of the assets, we extracted the logarithmic returns. Important that they are logarithmic because then they are time additive. And well, we had to do some pre-processing sometimes of the data. Sometimes the data, let's see. So sometimes we were able to fit all the data into the processor or into the algorithm. That was the case of Tensor Networks, okay, because we could handle lots of variables, also in the wave hybrid. But sometimes say the quantum processors, they were limited to only 12 qubits, and to fit the data into there, we need to do some pre-processing sometimes. What we did, we noticed that it was interesting to do a clustering of the assets. So for instance, here you have an example where we picked up a number of assets and did a clustering into 6 different classes. And it's, there are lots of classical clustering algorithms that you can use here. And, once you have this clustering, essentially what we do is, we redefine some kind of effective asset taking into account the clusters, all right? Here is how the variance goes down with the number of clusters. Of course, the more clusters you include, the less correlated they are. Good. Then in order also to do a fair comparison of different methods and hardware platforms, we did different data sets. We used 6 different data sets of increasing size. Here is the summary from XS to XXL. This looks like, like clothes. The total number, the 2 important rows here are these 2 ones. Here is the total number of qubits for each asset. Okay, so we went from 6 up to 1,272. And now the solution, the size of the solution space, it's of the order of 10 to this number. Well, it's actually 2 to the power of this number. And you know that we go from 64 to something of the order of 10 to 388 and 82, which is, starts to be already very large, okay? And well, the time here was taken in business modes, but well, that's maybe less important. Now, what is important is that the size of the solution space is growing up exponentially fast. And for excess, for a small number of qubits, this was fine, but as soon as you start scaling this up, the problem blows up, okay, as in here. You have 10 to the 382 different possibilities. If you want to solve this problem by, brute force, there is no way. Okay, so here is the summary of the results. There is a lot of information in this slide. So in this table, we have 3 different quantities that we computed: Sharpe ratio, profits, and runtimes, all right, in seconds, for the different algorithms and for the different data sets. Now, wherever you see a dash means that we couldn't make it. The algorithm couldn't make it. We could make it, not the algorithm. Okay, so So it means that there was a limitation here. And here you can see very clearly what is going on. So for instance, with BQE on IBM-Q, we were able to solve the problem for the excess data set. For S, it was already too much. For the exhaustive, we arrive up to S, BQE constraint and so on. And at the end of the day, we see that the two techniques that allow us to solve the bigger problems are D-wave hybrid and also tensor networks. Now, there are a number of things that must be said about these results because there is a lot of information in these tables. The first one is that not all figures of merit are equivalent. This is something that we noticed from our simulations. And this is an example. We want to optimize the returns, okay? And then, for instance, if you focus on the XXL dataset, you will say, well, D-wave hybrid is doing fantastic, 67%, okay, of returns. That's super good. But then you say, but what is the algorithm that is maximizing my Sharpe ratio? Well, then it turns out that Tensor Networks is doing better. Okay, you get lower returns, but you also have a lower risk, let's say. So this is interesting. We noticed that from our simulations that not all figures of merit are equivalent, all right? We also noticed that D-wave hybrid works very well, and also Tensor Networks. They allow us to solve the largest possible sizes of the problems. D-wave hybrid is extremely fast. So if you have a look at the runtimes, the XXL dataset was solved in less than 3 minutes. This was very fast, all right? If you have a look at the running time of Tensor Networks, you could say, wow, this is scaling up like pretty bad. But this was using my laptop, okay? The point about Tensor Networks is that this was version 1.0 of the algorithm. And we know already how to improve these several orders of magnitude. First, by modifying the structure of the algorithm. Second, by using, say, GPUs. Okay, using graphical processing units, we can speed up Tensor Network algorithm easily by a factor of 10, and also using other tricks, all right? So this number here is, it's just the first one that we computed, but we already know how to bring it down quite a lot, right? Then we also saw from our simulations that, variational quantum eigensolvers, they are a very good option for optimization problems. But if we have to run them on relatively small processors, then they are limited, all right? So, with BQE constraint, we managed to go up to the data set of size M, but with plain BQE, this was very restricted, okay? So one needs to invent hybrid algorithms or more complex hybrid algorithms, in our opinion, to be able to put real data into these processors, all right? It doesn't mean that it cannot be done. Of course, it can be done. There are many ideas that one could use here. You could concatenate chunks of quantum processors and then reshuffle the. I don't know. There are many things that can be done, but if you just try to apply plain BQE, you cannot compete with, say, the wave hybrid. No, you can see it from here, at least for this problem. Okay. Good. Now, the nice conclusion from here is that this was the largest portfolio optimization so far with quantum and tensor network methods. And it was also using real data. So this was real. So we didn't generate random data here. This was real data, which, it was provided by us. And which is, it was a real optimization. So these profits are real. Okay. Good. So what's next? Well, there are a number of things that one could do here. One could add more complicated constraints. Here, the list of constraints could be infinite. One could improve the hardware. Of course, if there are more qubits coming in the new IBM-Q processor, then fantastic. If there are also new quantum processors coming from D-Wave, then also fantastic. And one could also improve the algorithms themselves. So one could think about new strategies of hybrid quantum classical algorithms for solving optimization problems. One could find more efficient tensor network algorithms, and also for these quantum-inspired algorithms, implementations on high-performance computing, on graphical processing units, on FPGAs, and so on. All this is going to bring acceleration, for sure. So my conclusion is that the results are starting to look like very promising. We managed to solve this dynamic portfolio optimization problem for a very large data set and for many qubits with real data. But this is, this is a lower bound. Things can only get better from here. Good, and I think I'm already on time. Last but not least, let me just say one word about Multiverse. Multiverse Computing, this is a startup that we are running here in San Sebastián, but also in Toronto. We have the headquarters in beautiful San Sebastián next to the ocean, so we can go surfing, but we also have people in Toronto where there is a quantum hub of growing very quickly. We have a number of partners and we have institutional support. And yeah, if you are interested in what we are doing, just let me know. Thank you very much.
Thank you, Roman. This was a very nice presentation. Let me actually start with a few questions myself, since there was one question in the Q&A, which is more of a clarifying question, which I addressed actually. Just a simple thing to note, a few things. I'm going to start as a finance person. This is a comment that my colleague Andrew Babi made, who's actually online. You do need to discount in your Hamiltonian. $1 today is not the same as $1 tomorrow. You're basically not, but that's just a rewrite of the cost function. But a little bit more deeper is your mu t's and sigma t's, your expected returns and your risk, they're predetermined from what I gather. And in fact, over your investment horizon, your sort of sigma filtration assumes that you have all the future values of expected returns and sigma, there is a little bit of a false impression, I think, in how you look at the number of assets, the number of time periods, and the number of qubits. You kind of didn't take that product when you take a look at that. It gives you the impression that you can trade off time with assets, but that's not quite true, actually.
No, not really. So you may end up with the same number of qubits, but a completely different Hamiltonian. So yeah, that's true.
Also, the risk calculations, the sigmas grow on you, which you sort of have as given, but they grow on you as you increase the number of assets, say. Yeah. So there's not real. There's a non-trivial trade-off. Have you sort of looked at that?
No, we didn't. We didn't. So we just took it was calculations using past data. Right. So only from this data, we just extracted the returns, okay, and then the fluctuations. But there was we didn't add any noise or no.
The other thing, I'm a little bit surprised why you use clustering. I mean, most of the the quantum implementations that I've seen, I mean, they all resort to dimensionality reduction, which is sort of essentially what you're doing. But most of them go via principal components. One is it kind of has a relationship with tensor structures, and so that's nice. But secondly, of course, in finance, we are thinking of factor models and exposure to factors, and so it's a more natural dimensionality reduction as opposed to your cluster, which I find not so appealing, actually, because you end up, I think, with 6 clusters, and then you basically invest the same amount in the stocks that are in each of the clusters, et cetera, or assets, I should say.
Yeah. No, that's true. There are more complicated, there are more complex way of reducing dimensionality. This we didn't try. We used clustering because it was like, it was kind of a very natural option that we saw coming from physics. We saw that lots of assets were just behaving very similarly, and then we just ran some plain clustering algorithm to reduce dimensionality. But I agree, there are more complicated ways precise ways of doing this.
Yeah, I agree. You should know that when you fix gamma, you can maximize the Sharpe ratio. So it's a special case, by the way, of your optimization. I don't know what you picked for gamma, the gamma, at least in the case without the transaction cost, etc.
Exactly.
It's a special case.
So if you don't have the transaction cost and you fix gamma equal to, I think it's 1 or 1/2, something like this. This is the same story as the Sharpe. This is like optimizing the Sharpe ratio. Yeah. But if you add the transaction cost, then the problem becomes suddenly much more complicated.
I agree.
Because you have correlations between different times. Okay.
I agree.
And this makes the problem much more complex. Yeah.
In your tables, your Sharpe ratios I would like to see them per unit of time.
Okay.
Because they're not comparable, right? I mean, you had a long conversation about some of your numbers are not comparable because they're on different platforms and blah, 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 different speeds. But also from a finance point of view, those Sharpe ratios are over different periods. And you want to have per unit of time, I think, a comparison. Otherwise, it's kind of apples and oranges, I think. And the other thing, why not compute this as continuous weights on a classical machine? It's a quadratic optimization problem, right? I mean,
I agree.
it's not so difficult. And the reason why I'm saying that is that, you know, we sort of have very accurate ways of solving this.
Yeah.
And I would actually just look at whether the quantum machine achieves the same solution.
Yeah.
And in fact, without transaction costs, we have an analytic solution. You know, mu t times sigma inverse times gamma over 2. You know, why not?
We discussed it in the paper. I agree. We just stick to the discrete formulation because it's kind of very natural. You know, you just work with qubits and that's it. But I agree that if you just let your weights to be continuous, I mean, if you don't have transaction cost, it's exactly solvable. If you add the transaction cost, then, you know, it's kind of more complicated. You have to solve all these systems of partial differential equations, I think, and so on. But you could also do it with a quantum computer. Yeah, why not? So that's something interesting that we, as far as I know, nobody tried. So.
I mean, it's a time-separable quadratic optimization problem, from what I've figured out. I mean, that's not too complicated.
No. I mean, there is a set of equations that, well, depending on how your assets behave, they can, you know, be a bit complicated. But the analytical structure is very clear. I agree.
So it sounds like we don't have too many questions. Anybody has desire to shoot off a question? Doesn't look like it's a timid performance today. So where do you see, actually, since we have a little bit of time, where do you see your clients? Oh, there are actually questions coming in, but let me just finish that question and then we'll feed some of the questions. You kind of mentioned derivative pricing.
Yeah.
You mentioned portfolio allocation, which is what you really talked about today. You mentioned machine learning. When you talk to financial institutions, what excites them most?
Well, right now they are very interested in optimization. Okay. Perhaps because, you know, this D-wave machine, with D-wave, one can solve problems that are larger than, let's say, with other universal quantum processors, because, you know, one has to understand also that the quantum processor of D-wave is different, all right? You know, they don't have so much control on the noise, temperature, whatever. I mean, it's a different story, all right? But they so far they look very interested into optimization problems, portfolio optimization. Yeah. There are also some people that are interested in you know, applying quantum machine learning techniques to problems such as, you know, fraud detection, money laundering, and so on.
Right.
This is also one of the applications that are going to come first in quantum computing, in my opinion, because for quantum machine learning algorithms, for obtaining good quality solutions, or at least things that are not so obvious to obtain with a classical algorithm, with already few qubits, it's already fine. So you can, let's say, you can already do things with few qubit processors, and that's exactly what we have nowadays. And of course, they will be very excited to do option pricing. The problem is that for those algorithms, one needs high quality qubits, processors that are very large and so on. With this quantum amplitude estimation algorithm that I was saying, for that you need very good and big quantum processors, and that, well, unfortunately, we still don't have it. No, so I will say that on the short term they are focusing more on optimization and let's say quantum machine learning. So things like fraud detection, classification, and so on.
Question from Dan Stansel. Out of curiosity, which IBM-Q processor did you use?
Oof, I don't remember the name, but it was one with 12 qubits. Okay.
Okay, I think I forgot which one that is. One too, actually.
Yeah.
Is that Kupix? No, is that.
I don't remember. So one of the collaborators, so Sam Mughal, one of our collaborators, also in Multiverse, so he was the one taking care of these BQE simulations on IBM-Q. He told me that he used the 12 qubit one, but I don't remember the name.
Perhaps it's the Tokyo machine, if I remember correctly, or I might be wrong on that. The big issue, another question is, the big issue that I see is that the logic presented is, I need a quantum computer because the optimization I need is NP hard. It's NP hard only because I'm accounting for the discreteness of the shares. So it's kind of the criticism that, you're formulating as a discrete problem.
Yeah.
And I understand why you're doing that, to get sort of in a qubit setting. But bloody hell, why not look at it? It's sort of what I said in the beginning as well.
I totally agree. So if you don't have transaction cost, if you don't discretize, you have an exact solution. But if you discretize, then it's NP hard. So why discretize? On the first place. Now, if you have transaction cost, then it's a different story. Then I think it's NP hard anyway. But because at the end, if you have to solve the partial differential equations on a classical computer, you have to discretize them. Or at least the computer is going to discretize them at a bit level, let's say. So, but I agree. I have the impression that the continuous problem is easier than the discrete one. Now, some people like the discrete one, some other people prefer the continuous.
Yeah, I mean, we can have a discussion longer on this. It's still, as I keep saying, it's still a quadratic optimization problem. The first order conditions are linear, so that's fairly easy to solve. Once you get into risk functions that are outside of the quadratic Markovitch framework, then constant relative risk aversion, risk functions, etc. Those are a little bit nastier to deal with. Still manageable. Follow-up question is, the modeling of transaction frictions is a little bit too simplistic. Again, it's quadratic. You stick to that. Why not work with realistic transaction cost models that are usually too hard to work with in classical optimizers?
Well, we could also consider that. This was the first thing that we considered. But, from now, we can just start complicated things. So if there are other more realistic and complicated transaction cost models, then perfect. We'll think of a way of implementing them as well. Yeah. But this is what I was saying at the end. No, so now on top of this, one can start adding more realistic conditions. Market impact, for instance, we didn't consider that here. What happens if I do a very big order? No, I move the whole market. This we didn't put it on the equation, but we could do it. So yeah.
We're running out of time. This was fun. I'm going to close with a few other things. Since you mentioned amplitude estimation, I have the pleasure to announce that our next webinar will be on November 19th by Tomoki Tanaka from Mitsubishi Financial Group and Keio University in Japan. He's going to actually talk about maximum likelihood amplitude estimation on noisy quantum computers. We also have webinars scheduled for December and for January. We will be posting them on our webpage. Thanks again, Roman. This was fun. Thanks to all of you out there. The paper is, as Roman mentioned, it's available on arXiv. So until November 19th, thank you again for participating. And thank you, Roman. Take care. Bye-bye.